Alright guys, welcome back to another segment of GGTutoring. Today I'll be covering like cyclohexane and its chair conformations and ring flips. I know most of you guys probably have your exam 2 coming up for Chem 343, so I hope this is some good review for you guys. So on the left, I've drawn just a very basic model of what a chair conformation of cyclohexane may look like with the different hydrogens projecting out of these different carbons. And the ones in the darker brown are your axial hydrogens, and these can either go straight up or straight down. And the ones in about the lighter orange are your equatorial hydrogens, which kind of go at more of an angle. Those also can go up and down, but its orientation's a little different than the axial hydrogens because it kind of goes out a little bit more than just straight up and straight down. So these are your equatorials. On an assessment, you're not going to see anything kind of like this. This is just a very basic idea to kind of understand what a cyclohexane may look like. But for example, I've drawn the little skeleton structure of methyl cyclohexane from the top down view, and sometimes you're going to have to try and convert this into a chair conformation. So this wedge coming out is your methyl group. And basically to draw this, so I'm going to start by drawing this into a chair conformation, basically. So you want to draw two parallel lines going like this, and you're going to draw another two parallel lines, and then this is going to come out like this, and this is going to go down like this. And it doesn't really matter where you add this methyl group into. It's just that you're consistent when doing the ring flips. So it's easier to kind of just label your carbons. So let's say that this methyl group is on carbon 1, and you want to just go in like a good pattern. So it's probably better to go clockwise. So carbon 1, carbon 2, 3, 4, 5, and 6. So on this chart conformation, we can just say that this is carbon 1, and then we can say this is 2, 3, 4, 5, and 6. And because this methyl group is on a wedge, it's going out of the plane and up. Whenever you see a wedge, you want to think going up. It could either be axial up or equatorial up. But if it's on a dash, you want to think of down. So that could be axial down or equatorial down. So in this case, it's on a wedge, so it'd be going up. So starting on carbon 1, you would draw your methyl group going up, like an axial up, okay? And I'll just label that for axial up. So when you're doing a ring flip, basically you're inverting this cyclohexane right here. So I'll draw the ring flip, and I've written this up above to kind of keep in mind. So when you're doing ring flips, every axial group will turn to equatorial, every equatorial group will turn to axial, but its orientation stays the same no matter what. So let's say that it was axial up, it would turn into equatorial up. Up always stays up. That never changes. You can never go from up to down or down to up. So when we're doing a ring flip, up stays up and down stays down. But the axial and equatorial changes when you do a ring flip. So basically the way to do this ring flip is kind of draw these two parallel lines a little bit different, like the opposite direction, like so. And you get something that looks like this, where it kind of changes the orientation a little bit. And basically when you're doing ring flips, the easiest way to do it is, you see how I've drawn, so I'm going to circle this carbon 1 that I've done. It's going to move down clockwise. Whenever you do a ring flip, just move your carbon numbers, the carbons that you've numbered, in the clockwise direction. So where I've circled 1, this is now going to become carbon 1. This will be carbon 2, 3, 4, 5, and 6. It's very simple. It's just remembering that when you do these ring flips, just move all the carbon numbers 1 to the left or just in the clockwise direction. Okay, guys? And because this methyl group was in the axial up position, it's going to change to equatorial up because axial goes to equatorial in a ring flip, and the up orientation always stays the same. So I'm going to draw what that looks like. It's going to be equatorial and up, so it's going to look something like this. And I'll write it down. This is equatorial up. But now, you might have, in some assessments and exams, you're going to have to determine equilibrium. So when you see these two rings are common in nature, but one's going to be more favored than the other. Generally, the equatorial groups are much more favored than the axial because of sterics. Because, let me draw for example, this carbon 6 is going to have two hydrogens kind of coming out, and you can kind of see that there's going to be some steric repulsion going on here. But in equatorial, it's a bit farther away from these hydrogens coming out, so it's much more stabilized. So we can draw the equilibrium something like this, where it's more favored, like this. And sometimes when you have more groups, like more substituents than just one methyl group, you want to determine their A values. So for Chem 3D43, the exam reference sheet lists all the A values you need to know. So you don't need to memorize these A values, but you want to be familiar with like basically groups that are bigger and bulkier. You want those groups to be equatorial compared to axial for more stable products, basically. So this is basically just like the basics of a chair flip. I'm gonna go down to some few more examples I've drawn down below. So we have this molecule with two substituents. And since one is on a wedge and one's on a dash, you know that these substituent groups are trans to one another. Okay? So I'm going to start out by drawing this chair conformation. And we can just say that our phenyl group is going to be attached to carbon 1 because it's probably the biggest group, so you want to probably label it like that. 2, 3, 4, 5, 6. You can label this as carbon 1, 2, 3, 4, 5, and 6. And since it's on a dash, it would be going down. So we can say that this phenyl group would be axial down. And then since our next group is on carbon 3, you would skip carbon 2, obviously. And since it is on a wedge, it'd be going up. So this would be equatorial up, as shown here. So when you do your ring flip, you're going to get a structure that looks like this. And you're going to go clockwise. So this would now become carbon 1, 2, 3, 4, 5, and 6. Your phenyl group is now going to go from the, this was axial, this was axial down, and this was equatorial up. So now your phenyl group is going to go to equatorial and down now. And then this group on carbon 3 is going to go to axial up now. So how do you know which one's going to be more favored now? Because you have two substituents. This is a CH3 group. There's three carbons here, another carbon right here, and each of these carbons extending out have 3 hydrogens. And this has an A value of 4.7 to about 4.9, and our phenyl group has an A value of 2.8. So you want the group with the larger A value to be equatorial rather than the group with the smaller A value to be equatorial when you have a choice. So you can see that our bigger group is equatorial here, and our phenyl group is axial down here. But then on the right, your big group is axial up, and your smaller group is equatorial down. So because of knowing that the group with the bigger A value should be equatorial, be favored, our our equilibria will look something like this, where it's favored towards the left, okay? And now I'm going to go through just one last example, just carbon 1, 2, 3, 4, 5, and 6. Draw the ring real quick. You have a wedge, so this would be your methyl group going axial up. You have a dash now, so this would be axial down. And then you have a wedge which would be going up. And then if you're gonna do this ring flip, you're gonna get something that looks like axial up now goes to equatorial up, so it looks something like this. Axial down is gonna go to equatorial down, so you'll get this. And axial up is gonna go to equatorial down, like so. And now we can look at our A values that are provided on our reference sheet, and we know that each CH3 group has an A value of about 1.74, and a C2H5 has an A value of 1.79. And this makes sense because our C2H5 is a much bigger substituent than CH3. So if you're running out of time and you're not able to look at your A value sheet for some reason, try and think a little bit logically about which molecule may be bigger, and then you can kind of figure out the priorities of A groups. So in this case, this equilibrium would be favored towards the right, because the bigger group is equatorial in this case, but it's axial in this case. So that's basically all I have to cover about cyclohexane and different substituents for chair conformations and ring flips. I hope this video made this concept much more simple for you guys and is some good review for your guys' exam tomorrow. And if you have any other questions, please feel free to drop them down in the comments below, and I hope this video was helpful again. Thank you guys.